All right, number 6 here. This is a yellow light given off by a sodium vapor lamp used for public lighting. Has a wavelength of 589 nanometers. What is the frequency of the radiation? So we know frequency is equal to the speed of light over the wavelength. Speed of light is 3 times 10 to the 8th meters per second. Wavelength, we rewrite it as 589 times 10 to the negative 9th meters. Okay, and so when we divide this here, we get 5.09 times 10 to the 14th hertz for the frequency. Part B is asking what is the energy of one photon. So we know the energy of a photon is equal to Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds times the frequency. So we multiply the numbers together, we get 3.37 times 10 to the negative 19th joules, and that's the energy of one photon of sodium. So part C here is it's asking, is the energy of a sodium vapor light higher or lower than the energy of ultraviolet light? So you probably should know that the energy of sodium, if it gives off it says a yellow light, so it gives off a yellow light, it's in the visible region. We know that anything wavelength from 400 to 800 nanometers is in the visible spectrum. And so we should be able to see it versus UV light, which is in the 200 to 400 nanometer range. We know that has higher energy, and so a sodium vapor light should be lower in energy than ultraviolet light. And I went ahead and proved it mathematically. So I picked a wavelength in between this range here, 250 nanometers, and then calculated the frequency, which is the speed of light over the wavelength, converted in meters. And that's 1.2 times 10 to the 15th hertz, or per seconds. And so if I take that number and multiply it times Planck's constant, I can calculate the energy of this UV light here, which I found to be 7.95 times 10 to the 19th power, and that's in joules. So this number is actually larger than the sodium, the energy from a photon from the sodium lamp. And so because this value is larger here, we know the energy of the sodium vapor light is lower than that of the energy from ultraviolet light, which I proved here. You don't have to prove it, you could just say higher or lower, that would be fine too. Number 7 says write the formula for the given name. So here they gave the names for different compounds. Iron 2 bromide, so iron's plus 2 because it has Roman numeral 2. Bromide comes from bromine, it has -1 charge. Okay, so to balance out the charges here, which is the hard part when you're writing formulas, a lot of students forget to balance out the charges. Here, if it's iron's plus 2, I need a -2 for an overall charge of 0, so I need 2 bromines there. Potassium chloride, potassium's +1, chlorine is -1. It's a halogen, the chloride ion is a -1. So I just need one of each, so it's just going to be KCl for its formula. Dihydrogen dioxide, so the di prefix means 2, so I need 2 hydrogen and 2 oxygen atoms, so it's going to be H2O2. Part D, sodium phosphate. Sodium is +1 because it's group 1. Phosphate is a polyatomic ion, PO4 with 3- charge. Okay, so to balance out the charges here, we need 3 sodiums to balance out the -3 of the phosphate. So it's going to be Na3PO4. Part E, lithium hydroxide. Lithium is +1 because it's group 1. Hydroxide is a polyatomic ion. Its formula is OH -1. So you need one of each, so it's just going to be LiOH. Part F, gold 1 iodide. Gold has a +1 charge as indicated by the Roman numeral. Iodide ion has a -1 charge, so it's just going to be AuI. All right. Okay, number 8 here. So it says, consider the following reaction. You have 2 molecules of ammonia yielding 3 molecules of hydrogen gas and 1 molecule of nitrogen gas. So in this problem, you're having to estimate the bond enthalpy given the values for each type of bond. It says you may have to use a Lewis-Dot structure to determine the bond order. So what I did was I looked at the formula here, okay, the chemical formula. I wrote out the Lewis-Dot structure for ammonia, okay, which looks like this. So you notice there are 3 nitrogen-hydrogen bonds here for each molecule, and then there's 2 molecules of that. So that means there are really 6, right? 6 NH bonds, okay, for 2 molecules, to represent 2 molecules of ammonia. There are 6 bonds there that have to be broken. Each bond, NH bond, is 391 kilojoules per mole. Okay, so 6 times 391 is 2,346. And then for my products here, I have 3 hydrogen-hydrogen. I have 3 molecules of H2. So each H2 has 1 HH bond. Okay, so there's 3 HH bonds there. So if you look at this table here, that's 436 kilojoules per mole for all 3 of those. Okay, times 3. All right, so 3 times the 436. This 436 is just for 1. Okay, so 3 times 436 here, plus 1 N2 molecule. So N2 actually has a nitrogen-nitrogen triple bond. Okay, so 1 nitrogen-nitrogen triple bond. So I looked that up on my table. On the table here, it says triple bond, nitrogen-nitrogen triple bond. Is hard to draw. Is 941 kilojoules per mole. So 1 times 941 kilojoules per mole. All right, so it's the formula here to find the enthalpy. Bond enthalpy is going to be equal to the summation of the bonds broken, bond enthalpy added up together for all the reactants. Here there's just one reactant, ammonia. Okay, so it comes up to that number, minus the summation of the bond enthalpy for the bonds formed, okay, for the products here. And so we have 3 hydrogen-hydrogen bonds and then 1 triple nitrogen bond. So we add those together to get 2,249. So the difference between those two values is 97 kilojoules per mole. All right, so that's how you answer that question number 8. And then for the part B here, the table kind of spills over to the following page. And then the part B asks if the reaction is exothermic or endothermic. So the value that we found was positive 97 kilojoules per mole, so therefore it's endothermic because it has a positive enthalpy. All right, number 9 here, it's asking us to balance the equation. All right, so here we have 1 iron on each side, 2 chlorines, and 1 magnesium. So it's already balanced. It says write the net ionic equation. So here I kind of flipped it around on you here. I put it in the wrong spot. So here is the net ionic equation. So what I did was I wrote the reaction first, what's written up here. Okay, so to write a net ionic equation, what you have to do is you look at the subscripts here. If it's aqueous, you break it apart into ions, right? If it's a solid or liquid, you keep it together. Or here is a solid, so I kept it together. Here FeCl2 is aqueous, so I break it apart into ions, 1 iron plus 2 ion, 2 chlorine minus 1 ions. Magnesium chloride is aqueous as well, so 1 magnesium plus 2 ion, 2 chloride ions. Okay, and then iron is solid, so I just left it as it is. So notice my spectator ions here are the 2 chlorine ions on both sides. Everything else is different. Okay, iron went from +2 to 0, and then 0 to +2 for magnesium. So then I write what's left, okay, and that's my net ionic equation. which should be up here, but I flipped them. So it says that right here. All right, so it says the next thing is write the two half reactions, which I have up here. So what I did first, I assigned the oxidation numbers to each metal. So magnesium was uncombined, so it's 0 here. Iron's uncombined here, so it's also 0. Here iron is combined with chlorine. Chlorine's -1, there's 2 of them, so it's -2, so iron must be +2 here. Magnesium's +2 because it's group 2. Chlorine's -1. Chlorine did not change, and that's why it's a spectator ion further down there for the net ionic equation. But magnesium went from 0 to +2. Okay, so it lost 2 electrons. And then iron gained 2 electrons, go from +2 to 0. So magnesium was oxidized, it lost 2 electrons. Iron was reduced, it gained 2 electrons. Okay, so these are considered the half reactions. When they ask you to write half reactions, that's what you're having to do. You're splitting up the metals, and you're showing if either they're losing electrons or they're gaining electrons. Okay, being oxidized or being reduced. All right, part D, clearly identify the oxidation reaction. Well, I wrote it out here, okay, but you can also just label it, okay, and that's fine too. All right, number 10. Here we have different formulas. We're having to write the names for them. So it says, name the following compounds or ions. PO4 3-, that's phosphate ion. NaBr is sodium bromide. Remember, when you have a metal and non-metal, it's an ionic compound, and so then you have to see if it's a transition metal or not. Sodium's not a transition metal, so there's no need for a Roman numeral there. It's always +1. For the next one, though, CoCl2, we need a Roman numeral. There's a metal. Cobalt's a metal, but it's a transition metal, so you have to specify the charge. So that means you have to figure out what the charge is here. Because halogens are -1. 2 times -1 is -2, so cobalt must be +2 because there's one of them there. So cobalt 2 chloride is the name of CoCl2. KMnO4. K is potassium. It's not a transition metal, so there's no need for a Roman numeral there. MnO4 is permanganate ion. It has a -1 charge, so your name is just going to be potassium permanganate. All right, H2SO4 is sulfuric acid. All right, SO4 is sulfate 8, so sulfate 8 becomes ic, so sulfuric acid. KOH, K is potassium, OH is hydroxide, potassium hydroxide. That's a strong base, so that's the name for KOH. All right. Number 11, write the correct balanced reaction for the combustion of methane. So I know with the combustion reaction, methane and oxygen are the reactants. Okay. When I have a hydrocarbon combustion reaction, the products are always carbon dioxide and water. So here we have 2 oxygens, here we have 3, okay? So we're having to balance this out here. So if I put a 2 here, now I have 2 plus 2, I have 4 oxygen on the right. So I put a 2 here to make 4 on the left-hand side. I have 4 hydrogens on the left, I have 4 on the right, I have 1 carbon on both sides, and so it's balanced. So this is the correct balance equation for the combustion of methane. Part B, write the correct balance reaction for the neutralization of hydrochloric acid, or HCl, with sodium hydroxide, NaOH. Okay, and so this is a double displacement reaction where you have hydrogen and hydroxide coming together to form water, and then sodium and chlorine coming together to form sodium chloride. All right, so we have 2 hydrogens on both sides, we have 1 chlorine on both sides, and 1 sodium on both sides, so it's a balanced equation. And finally, the last question here, number 12. I did initially have the wrong answer on there because I think I changed the element. So this was cesium, and so electron configuration for cesium is going to end in 6s1. And so if we look on our periodic table here, cesium. So we're starting out, and nearest noble gas is xenon. Okay, and then it's going to be 6s1. And then the orbital diagram for that is going to be similar to electron configuration, except you're showing the electron, the orbital here, designated by a line, and then the arrow up indicates one electron spinning up. Now, if you put one single arrow pointing down, that would be fine too. Part C, write out the electron configuration for Cs+. So that's the noble gas configuration for xenon, or I wrote it if you wanted to write out something that a little more complicated than xenon, you could start with the shorthand for electron configuration for xenon. And part D, the Lewis structure for cesium would just be, since cesium is in group 1, it has one valence electron, right? So it would have one dot for a Lewis dot structure. And then the next question, the electron configuration for nickel. Nickel's right here, so its nearest noble gas is going to be argon, and then it's going to be 4s2, and then 3d8. So that's your answer for that one.